Today's warm-up question says 3 resistors, 2 ohms, 4 ohms, and 5 ohms are connected in series. Find the equivalent resistance. And then if they are connected to a 9-volt battery, what is the current in the circuit? And then what is the power supplied by the battery? So we're doing some of the calculations that we looked at the very end of yesterday's notes. We're going to go over this example, which is just one more series circuit, and then we are going to get into some more examples that include parallel circuits so that you can work on today's homework assignment 1104.2 series and parallel problem set. So here is a diagram of what is described in the warm-up, and that might be helpful if you want to draw a picture, especially if you're a visual person. So you may want to sketch something that looks like this. Could you draw it differently? Sure, as long as you connect them in series. It doesn't really matter if you put them in these exact positions. The first question is to find the equivalent resistance. And in a series circuit, that is really easy because it is simply adding together those resistances. 2 plus 4 plus 5 is 11 ohms. So this circuit with these 3 resistors is equivalent to a circuit with a single 11 ohm resistor. That's what that means, but it's the total resistance in the circuit. So the answer to number 1 in the warm-up is 11 ohms. Number 2, find the current. We did this yesterday. And to help us organize it, we used a table. And you very well may want to draw a table just like the one we did yesterday in our notes, or you don't have to have that. We can go ahead and just look at the information we do have. I know that if I'm trying to solve for current, I'm going to be using Ohm's law. And I know that I have the total resistance of the circuit and the total voltage. And so I can find that current leaving the battery, that total current, and that current is the same everywhere. So that's all I need is that value based on the total resistance and the total voltage. So I plugged those in. Voltage equals current times resistance. 9 equals I times 11. Divide both sides by 11. 9 divided by 11 is 0.82, and my unit, of course, is amps. The third question up here is to find the power supplied by the battery. We have an equation for power that we learned yesterday as well. Power equals voltage times current. We're going to use the total values for the circuit because it's asking for the total power from the battery. And so we have power equals, my voltage is in my diagram here. It was also in the question on the first slide, but it's 9 volts. And my current is what I just found in the previous question, 0.82 amps. If I multiply 9 times 0.82, I get a power output of 7.36 watts. Okay, so again, this is some of the same math we did yesterday. You don't have to draw the table to do this, but you could, especially if you're having a hard time keeping it straight and you want to make sure that you're using the correct values, because there are a bunch of different numbers on my screen, so you need to know how to use those. Does anybody have a question about the warm-up? Okay, so like I said, we are taking some notes today. Those notes are primarily going to be just some example calculations. We did most of the actual meat of the notes yesterday, which you probably noticed because we went through the whole period. But let's go ahead and we do have a little bit of notes before we get into the math. Let's go ahead and jot down. You can put it in a Venn diagram, you can put it in a T-chart, whatever you want. But you guys do need to be able to compare and contrast series and parallel circuits. You will see like concept questions like this on your quiz, on your test, potentially on your problem sets. And so again, you can put it in a Venn diagram, or you can make a T-chart, or you can just list it in bullets. I don't care, but I would write some of these things down. Okay, when we're talking about series versus parallel circuits, one of the most common things that you're going to be asked about is about what happens if you remove a light bulb from the circuit. Okay, it's something that you tested in the RA last week as well. And it's the thing that's listed right here. In a series circuit, if you were to remove that light bulb or any component of your circuit, all of the charges stop moving. The current stops flowing because you no longer have a closed conducting path. You have to have a voltage source and a closed loop to have current flowing through a circuit. And so if you remove a light bulb, you no longer have a closed loop, you have a gap. And so if you remove a bulb from a series circuit, current stops, all the bulbs go out. However, if you remove one of those bulbs or any component from a parallel circuit, from one of those parallel loops, yes, the bulb you take out obviously won't light, but the other bulbs will remain lit. Okay, so that is one of the more common things that you might see in a multiple choice question on a test, for example. So again, in a series circuit, if you take out one bulb, none of the bulbs light. In a parallel circuit, if you take out one bulb, all of the other bulbs will still stay lit. And that is because of this. The top thing right here is the definition. In a series circuit, there is only one pathway. So if you break that path, there's nowhere for the charges to flow. They can't make it through the other bulbs either. But in a parallel circuit, there are multiple pathways. So if you take out that bulb, yes, you break that one loop, but you have, let's say, 3 loops in your parallel circuit. Depends on how many resistors you have. In a series circuit, and I don't know that we'll ask you about this, but your batteries will last longer. And again, we talked about that voltage drops that we saw, those changes in that electric potential energy for each of those charges as they moved through. And in a series circuit, or in all circuits, the voltage drops along the loop add up to the battery's voltage. So in a series circuit, they are just, if you have a 9-volt battery, your voltage drops add up to 9. In a parallel circuit, let's say you have 3 loops. Well, you have 3 different loops, and so you have 3 different 9-volt voltage drops, for example, and so it's going to make that battery run out faster. So series battery lasts longer, parallel it would die faster. They both need a battery. They both must have a closed loop, no gaps. Again, this is the definition, or the requirements rather, for a circuit to function, is that you have to have a source of electric potential difference, or a voltage source, a battery, however you want to call that, and that you must have a closed conducting path, or a closed loop that has no gaps in it. So again, just some basics that we've already talked about together yesterday, that you've also seen in the FET that you did last week, and that you were investigating hands-on in the RA last week. So none of this should be new, but you may want to jot it down. This is not new either, because we talked about this yesterday, but I wanted to just remind you real quick of Kirchhoff's laws. We have the loop rule and the junction rule. And again, the loop rule stated that the voltage drops at the resistors or bulbs along a loop must add up to the battery's voltage. I just mentioned this one a second ago when I was talking about the lifespan of the batteries. But in a series circuit, because you have multiple resistors on the same loop, then they will all add up to the battery's voltage. However, in a parallel circuit, because each of your resistors is on its own loop, they're not adding up with anything. Each loop only has one resistor. And so at each resistor, your voltage drop will be equal to the battery, which means they're all equal to each other. The junction rule states that the current leaving the battery must equal the current returning to the battery. Technically, it says the current going into a node or a junction is equal to the current coming out of that node or junction, but that would also mean this. But it's conservation of charge, meaning that you have the same number of electrons flowing through that circuit. They do not get used up. They do lose energy, but the number of them remains the same. This is basically conservation of matter. This is basically conservation of energy. The loop rule is. But back to the junction rule. In a series circuit, that means that your current stays the same everywhere because everything is on the same loop. So pick 2 points. The current going in is going to be equal to the current going out. And then to the next point, same thing. Okay. In a parallel circuit, however, because you have junctions where your circuit splits and part of your charges go one way and part of them go the other, the number of charges that are going into each branch of that junction, they're going to be equal to the number of charges that come back together at the end. And so you're going to have the same amount of current returning to the battery that you had leaving the battery, or going into a junction that you have coming back out of the junction. In a parallel circuit, that means all of your loops will add up to give you that total voltage, and it's going to stay the same because along each loop you have conservation of charge. So just a quick reminder, because we're going to apply these rules today to a parallel circuit. Okay, so Again, yesterday we did an example with a series circuit. Now we're going to do an example with a parallel circuit. If I were you, I would copy this down in my notes so that I have it to look back at, especially as I'm trying to work through similar problems in today's problem set. This one says fill in the table with the resistance, current, voltage, and power for each resistor in the circuit and for the total circuit. Again, you might want to draw a table like this every time you approach one of these problems until you get more comfortable with it. Even after you're comfortable with it, this is still a helpful tool, so you could still draw something like this. But I have only 2 resistors in this circuit, so I have only 3 rows really, because I have 1, 2, and then my total. And then we're going to label the resistances, current, voltage, and power. So let's start with the resistors because they're in the picture, and they usually are. Okay, so you can almost always start by filling in those resistors. So we're going to find the total circuit values first, and we're going to start with equivalent resistance. So I have here 2 resistors, 2 ohms and 4 ohms. Okay, and if I take a look at this circuit, this is not a series circuit. I can't just say, well, 4 plus 2 is 6 and be done with it, because that's not how you find it in a parallel circuit. Remember, when I add more resistors in parallel, my equivalent resistance goes down, not up, because I'm also adding another pathway. Think of it like a road. If there's only one path, like in a series circuit, you're going to have a lot of traffic. Your flow of cars will be slow, smaller current. If, on the other hand, you have 2 different ways to get somewhere, or maybe there's 3 or 4 or 5, obviously as you add more roads that get where you're going, you're going to have less traffic on each of them. It's going to increase the current. Okay, so here I know that my total resistance will be less than 6, and it will be less than each of these individually, but we're going to solve it with the equation we learned yesterday. 1 over RT equals 1 over 2 plus 1 over 4. Okay, again, guys, some of you yesterday were working ahead and you weren't going over this example or the one that we did yesterday together with me. Please copy this down so that you're not asking me the same questions that I'm about to go over. Okay, again, when we add these, adding fractions requires a common denominator, or you can add it in the calculator, but this one is really easy to do by hand, so let's go ahead and just do it that way. Okay, now my common denominator between of 2 and 4, okay, because those are my denominators, I'm looking for the least common multiple, which of course is 4, and so I can write this instead as 2 over 4, that's the equivalent to 1/2, plus 1 over 4, which is 3 over 4. Again, that is not your answer. Some of you yesterday were trying to type that first value in as your answer, and that's not what you want. Okay, you need to get RT. This right now is 1 over RT is equal to this, which means if 1 over RT equals 3 over 4, flip both of those fractions and you have RT equals 4 over 3. 4 over 3 is 1 1/3, or 1.333333. Of course, that keeps repeating. I rounded it to just 1.33 ohms. Okay, so this is the equivalent resistance of this circuit. Notice it is smaller than these resistors are separately, because when I added another resistor, I decreased my total resistance rather than increasing it, because this is a parallel circuit. All right, so let's go back to that table. Okay, you'll notice I filled in my 2 and my 4. I filled in my battery voltage, and now I'm filling in my 1.3 ohms. Again, you can add more decimals, it just didn't fit on my screen. I do want to come over here real quick because I did fill in the battery voltage without really talking about it again, but this goes back to the rule we just talked about. The voltage drops along a loop add up to the voltage of the battery. I have 2 loops here. One of those loops contains a 2 ohm resistor, and that's all it has on it, so there's nothing to add to it. Its voltage drop is 10, there's nothing to add. The second loop also only has 1 resistor on it, this 4 ohm resistor, and so its voltage adds up to the battery, but again, there's nothing to add it to because there's only 1 resistor on that loop. And so that's why they're all the same value. Guys, every time you fill in a table for a parallel circuit, if it's a parallel circuit, those voltage values will be the same. the whole way down, okay, every time. Now, they're not necessarily always 10, but they are in this problem. Okay, but they will always be equal to each other if it's a parallel circuit. All right, so now that we have our resistance and we have our voltage, we can start looking at our current. But before we do that, I want to show you, and again, this is what I was just talking about. I want to show you this same electric potential difference diagram that we looked at yesterday, but for a parallel circuit. But before we do that, again, this is the same rule. In a parallel circuit, because each loop only has one resistor, the voltage drops will all be equal and they will equal the battery. That's what I just said a second ago. But here are those loops color-coded. In case you were having a hard time seeing it before, that's why I said it would be really helpful if you have different colored markers or highlighters or pens or something so that you can trace those loops. Okay, but the blue loop right here only has one resistor, so my voltage drop here is 10. The red loop only has one resistor. My voltage drop here is also 10. If I were to diagram that, it looks like this because each of these is on a different loop. So some of the charges get an increase in energy at the battery, and then they follow the blue loop, and then they lose that energy at the resistor. Other charges get an increase in energy at the battery, and they lose that energy at the red resistor because they follow that other path. Okay, and then they both make their way back to the battery again. So this diagram for a parallel circuit will always look like this because even if I added 4 more resistors, they would all have, if they were in parallel, they would all look just like that because there's nothing to add it to. In series, we had like 3 different arrows because we were adding them together. But here I don't have that. Okay, so if you're asked to interpret a diagram like this or to draw one, it's pretty easy for a parallel circuit. Okay, again, that's the first rule about the voltage. The second rule of Kirchhoff's rule says the current splits, so the total current of the circuit exists where all the paths overlap. So I have my total current here just after it leaves the battery, also over here where it comes back together, where I have both red and blue. Okay, it splits at this junction, and some of the charges go here and some of the charges go here. But again, the total amount of charge remains the same. They come back together over here. But the number of charges that go through this resistor is the same before and after, and then they come back together. The number of charges that takes this loop is the same going into this loop as it is coming back together at the end. Okay, that was the second of the rules. But it means that we can add together the loops to get the total, which is what we're going to do in a minute. All right, so back to our table. If I want to find my current, again, I can find my total current. I can also find these individual currents because I have voltages and resistances, and I can use Ohm's law. Again, Ohm's law is V equals I times R. I'm going to go ahead and solve for the total current. That's why I've highlighted it here in purple. So I'm going to use my total voltage and my total resistance. That's 10 equals I times 1.33. When I divide both sides by 1.33, 10 divided by 1.33 gives me a current of 7.5 amps. So that would be the total current leaving the battery in this circuit. So I'm going to fill it in. Okay, this current, when it reaches this junction, will split. Okay, now before I even calculate it, where will I have more current? Through the 2 ohm resistor or the 4 ohm resistor?
The same.
Not the same. I hear 3 different answers. I hear they're the same, I hear 2, and I hear 4. One of those is obviously right. There's a phrase we talked about yesterday. Okay? The charges prefer the path of, what do you remember what it was? Least resistance. Okay, so even before I calculate it, I know that more of my current will go here than here. Okay, so that 7.5 is going to split, but not evenly. More of it will go through the 2 ohm than the 4 ohm, but we can actually calculate that as well. Okay, so if we wanted to find just the current through the 2 ohm resistor, we could measure that with an ammeter. We could place it right here, for example. Okay, but we would solve for it like this. Again, going back to Ohm's law, V equals I times R will be 10 equals I times 2. Again, I'm just pulling the numbers from this row of my table. That's why the table might be helpful, because it helps you organize the numbers and make sure you pull the right ones. Of course, that means my current there is going to be 5 amps. Okay, so the current through the 2 ohm resistor is 5 amps. So the current through the 4 ohm resistor, I could either solve that using Ohm's law, or I could just subtract, right? Because I know that these two add up to 7.5. Okay, so I have two different ways that I could go about solving for this. If I wanted to solve just the current through this red loop through my 4 ohm resistor, again, I could place an ammeter at any point along this wire. I have it right here. And again, I could use Ohm's law, V equals I times R, 10 equals I times 4. I is, of course, 10 divided by 4, which is 2.5. Or I could have just done 7.5 minus 5. Still going to get 2.5 because, again, my total currents on each loop will add up. Or sorry, the current on each loop will add up to the current leaving the battery. So now I have all of my currents labeled. Okay, A3, if you had a question that put an ammeter here and it asked for the current at this point, you could simply add these two numbers together, or we've already found it down here. It is the total current leaving the battery. So the answer, if you were asked for this, would simply just be 7.5 amps. But you need to see how the questions might be worded, because oftentimes it'll just have a picture of an ammeter. It'll say, what's the reading at this ammeter? Okay, it won't say what is the total current. You would just need to know, hey, that's my total current. That's another reason why color coding your loops might be helpful, because you can see which ones are being read. All right, so again, technically the voltage reading across the battery is positive, meaning that my change in electric potential energy per charge here, that electric potential difference is positive, whereas it's negative at each of these. But you'll notice that I did not put signs in here, and we don't typically do that. But just as a heads up, you're gaining energy at the battery, you're losing energy here. It's dissipated from the circuit. That's why you get light and heat and all these other things that aren't electric potential energy. All right, let's go ahead and look at our power column. So to find power, we're going to use power equals voltage times current. As a reminder, we talked about this yesterday, power determines brightness. So when I find these, I will figure out which bulb is brighter. So let's go ahead and solve for those. Just as a little heads up, the brightest bulb in parallel will be where you have the least resistance. Note that that is the opposite of what we talked about yesterday with a series circuit. Okay, the reason that it's opposite is because in this case, in a parallel circuit, all of your voltage drops are the same. And so if power is voltage times current and the voltages are all the same, then it's really where the bigger current is going to give you more power. And the bigger current is, of course, the path of least resistance, which we already calculated our currents. So again, it ultimately comes back to power. But if you don't want to calculate power, you can think, okay, what's going to give me greater power? And it's going to be different in a series circuit than in a parallel circuit, and you saw that in your RA as well. Okay, so you can always come back to power, but brightest bulb in parallel will be least resistance. That is the opposite of a series circuit where the brightest bulb was the one with the most resistance. But in both cases, it's where you have the most power. All right, I didn't even calculate it here. So again, you can go and find these power values. This one would be 50. It's just 10 times 5. This one would be 25. 10 times 2.5. This one would be 75. 10 times 7.5, or 50 plus 25. Okay, so you can fill in the rest of that table. All right, here is another circuit. How many loops are on this circuit? How many loops do we have here? Yeah, we have 3. You can, again, color code them. There's 3. Okay, now I have blue, red, and green, but I have 3 loops. Okay. Without doing any math, which would have the greatest current going through it? Yeah, the 2 ohm resistor, path of least resistance. Again, you can calculate it too, but it will be the one with the path of least resistance. All right, guys, if you want to see that problem worked out for this circuit, I did it in the slides. I'm currently on slide 54. If you go to slide 55, you can actually click through that problem. So if you want to just look at one more example because you don't feel quite comfortable yet, please do that. Otherwise, what you're working on right now and for the rest of the class period is the assignment 1104.2, series and parallel circuits problem set. Okay, so again, if you want to look at another example, it is in the notes. We're just not going to go over it together because they do take a while to work out, and I want to give you time to do it if you feel comfortable with it. But if you don't feel comfortable with it, go back to those slides and click through it or ask for some help. Okay, if you do finish this early, you're welcome to get to work on the unit summary, which is posted in Schoology. But I'm going to let you guys get to work. If you have any questions, please let me know.